And then let me just see, recording started. Yes. So today we have Daniel Wrench, who is student of Tulsi Nandan Parasha from Victoria University, Wellington in New Zealand. So we have quite a bit of time difference. And luckily, this slot worked out good for both of us. And Daniel will talk about the basics of time series analysis. This is the part of analysis that has not been covered till now. And this is the first school where the time series will also be covered. And it's a very important set of data that one has, particularly in astrophysics, measurements which are time series. And Professor Tulsinandan Parasha is an expert on that. He's been working on for quite some time. I have the honor of writing one paper with Daniel and Tulsi on that subject. This was the early days of Daniel, and machine learning is everywhere. And but today, Daniel will talk about the basics of time series analysis for physics problems. So over to Daniel.
All right. Thank you for the introduction, Ritesh. Yep, glad to be with you all today. So yes, as introduced, I'm a PhD student here in Wellington. I've been working on various problems of statistical analysis of solar wind turbulence in particular. So fairly well acquainted with various issues in time series analysis. And I'll just give you a brief preview motivation for why this is important in one particular subdomain of astrophysics. So for example, there's this wind that comes from the sun called the solar wind, the stream of charged particles. There's various things we want to understand about how that flow becomes turbulent as it flows out through the solar system around the planets and eventually meets the interstellar medium. So one question is, what is the Reynolds number of that flow? You may be familiar with it. In some way quantifies how turbulent a flow is. So similar time series analysis we do here is computing power spectra, so looking at the distribution of energy across different scales. And with that, so you can see in this figure on the left here, we have that power spectrum, and from that, when we're studying turbulence, we're interested in things like the slope of that power spectrum. So you can see here with these dashed lines, here is the slope of that power spectrum in what's called the inertial range of turbulence, so where we see the self-similar behavior across different scales. So typically we'll collect a time series of the magnetic field of the solar wind, and from that we'll compute things like the power spectrum, we'll fit various power laws and compare those with theoretical predictions of how fluctuations should behave in a turbulent flow. And another statistic which we'll come across in this lecture is something called the autocorrelation function. And similarly, we can derive important turbulence parameters from that, something called the correlation length, or from what scale can we think of as the biggest eddies or biggest stirring motion in some turbulent flow, such as the solar wind. So those are the kinds of analyses that I work on, but unfortunately, time series analysis is not always straightforward. There's often a lot of problems with the data that make it difficult, and that is the specific thing that I've been working on for my research. So again, just motivating why this is such a rich topic of analysis, time series analysis. Here is some measurements from the Voyager spacecraft, which, as you may be aware, has now left the heliosphere. It's crossed the heliopause and it's now sampling the interstellar medium, which was very exciting. Our first in situ measurements from that part of the universe, really. Up until then, we've only been able to measure the solar wind in situ when it comes to astrophysical plasmas. But if you look at this data here, you see there are a bunch of flat lines or just straight lines joining data. Those are gaps. This data, because it's so far away, is highly sparse, and that causes a real problem when you're trying to do analysis of those gaps. And that's the specific problem I've been working on for my research. And the other big thing is you'll see this little bar here with the horizontal lines. that shows you the noise in those observations, specifically for this radial component of the magnetic field, which is what we're looking at here. So there's also a significant amount of noise. And as you may be aware, or you'll probably come across, noise is another major nuisance when we're trying to extract useful information from a time series. And things like signal to noise ratio, how you filter out various frequencies that you're not interested in, is a big topic, which we will touch a bit on later in the workshop. And then, yeah, finally, I might come back to this at the end, but the paper Ritesh mentioned that him and I and my supervisor worked on was looking at neural networks to try and improve the statistics we can calculate when there are significant gaps in those time series. So again, what we'll come back to later in the lecture is how machine learning can help with analyzing time series, given how prevalent and popular those models are. Okay, so there's a bit of motivation. So let's go back to my slides now. So yeah, what I'm going to cover ideally is firstly just an introduction to how we even define a time series in the first place, what we're trying to do with time series analysis, as well as some other examples outside of solar wind turbines, which is what I'm most interested in. What are other common ways of analyzing time series? And by the way, do feel free to ask questions during, if you feel like it, though there should be plenty of time at the end as well. So then after kind of setting the stage with some definitions and examples, I'll also work through some code. So we'll use Python and the main packages there to visualize and do some simple analysis of time series. Basically, how do you visualize it effectively to get useful information out of it? Then we'll look at a few of the different types of statistical analyses you can do. So you can measure things in the time domain, or very commonly in astrophysics, you'll convert to the frequency domain. So we can understand what are the most important scales of variation in our signal. And unfortunately, as in all robust statistical analysis, those types of analysis come with assumptions. You may have heard of this concept of stationarity. There's another one called ergodicity, which is quite important. So you can't go past looking at those, unfortunately, because those always are an important caveat or part of a robust analysis. And then, having described our signal, having extracted important information from it, we'll then move over to the realm of forecasting, because as you might assume, if you have a model that captures the variation of data well, maybe things will be predictable. Again, those have kind of classical or statistical approaches versus machine learning approaches. And then finally, I'll talk a little bit about noise and uncertainty, kind of nuisances that commonly have to deal with when we're analyzing real-world signals. Okay. So then moving on to some basic definitions. So what is a time series? Very simply, it's a series of points, series of measurements which are indexed by time. Okay, that's the crucial part. It's a sequence of observations. Now, when we're talking about statistical theory, time series is what you call a realization of a stochastic process. Now, a stochastic process is kind of the theoretical generalization of the time series, where the value at each time step is a random variable with some probability distribution. Okay, and when we take a measurement at each point, we're sampling from that distribution that we have at each point. Okay, so yeah, commonly stochastic processes are used as mathematical models of time series. White noise is a common way of modeling noise. Brownian motion, another one you might have heard of. But also, time series has a huge amount of overlap with the field of signal processing. Right, a signal is a time series itself. commonly we think of signals as being a time series of something like voltage, current, or some electromagnetic wave. But then really the epitome of what that sequential ordering gives us, which distinguishes time series analysis from probably the statistics you would have first learned at high school and university, is this autocorrelation between observations. And very intuitively, measurements which were made close to each other in time more likely to be similar than measurements made further apart in time. So this correlation with itself is autocorrelated, and typically expect that correlation to drop off as you get further and further apart. Now, and this is an important fact because you might also think, well, if you're taking measurements in space, you're also going to see the same phenomenon of autocorrelation. So therefore, a lot of the methods that we use for time series are also very applicable to spatial series because they have the same phenomenon of autocorrelation. Expect then you're dealing with 2D or 3D autocorrelation as opposed to just 1D, which is what we're focusing on here. And also, language is a time series. Language is a sequential process. If you can represent each word as a vector, so it's a multi-dimensional time series, I suppose, in that way. But yeah, that is also has this autocorrelation process, and large language models are in some way a form of processing time series data of this very specific sort. So that's what a time series is, and as well as that autocorrelation, that's mostly a given for the large majority of time series, other than white noise is the main example, which by definition has zero autocorrelation. These other properties may or may not be part of some sequential observations. They may or may not be periodic. You might see some clear seasonal trends. It may or may not be stationary. Again, that's a key assumption we'll come back to. And it may or may not be predictable. And again, if you have a model that fits your data well, that describes it well, then it may well be predictable. We'll come back to the end, comparing some different ways of modeling and forecasting time series. Okay. So some common examples of analyses in physics that you might be interested in. Big one is extracting dominant frequencies in the light curves of pulsars, which clearly show that periodic trend, which I just mentioned. Another one is detecting gravitational waves, and that is one where extracting signal from the noise is really the huge challenge, given how noisy these detectors are, and being able to match the waveform that you're after to what you actually observe is the key challenge there. As I already mentioned and gave some examples about, analyzing turbulence, the magnetic field of the solar wind is one where we need to analyze time series and use things like power spectra and autocorrelation functions. And then in terms of astrophysical prediction, you may think of some other ones, but the one that came to mind for me was trying to predict space weather. We would like to know when the next solar flare or CME is going to come towards Earth and knock out all our satellites. Hopefully not. And if we can create better models for those time series, perhaps we can get better at predicting. But obviously, there's a lot of physics that we need to understand to try and help with that. So finding the interface between physical understanding and modeling of data is a key problem when you're trying to forecast or do a lot of other tasks that might use machine learning that you can't necessarily explain. Okay, so those are some key applications. So now, for the rest of the lecture, I'm going to be running through some Python code to help explain the concepts and visualize them as we go. So start off by just going to reading an example data set. Okay, so first we're just going to read in our some libraries. And now, as their example data set we're going to deal with, we're going to use some measurements of sunspot numbers. So a very classic time series example is the sunspot counts over many centuries now. We have data for, we won't be using all of that. So we're just reading that CSV, and the important part of handling time series in Python, at least if you're using pandas, is setting this timestamp index. So you can see here we're extracting the variables which tell you the time associated with each observation, and we're setting that to a date time. And that's going to be very useful when it comes to plotting, when it comes to resampling, smoothing of the data. So very convenient to set your date time index and then make that the index of your object. Okay, so we will read that in. And then if we just look at the corresponding information of that, you can see there's a date time index, and it nicely tells you the beginning and end of that period. Okay. And once we do that, we can plot the results of our time series to have a quick look at it. And here we have our sunspot numbers. Now, what I'm actually going to do just quickly is just clear the output so that we can see them come up in real time. So let me just do that now. So, clear. Okay. Let's go back to where we were. Okay, so that was just our initial look at the time series, and you may have noticed that very conveniently you don't even need to specify the x-axis, because if you have that date time index on your data frame, it's very quick to plot the results and automatically render your x-axis and format it appropriately. So that's quite a nice feature of the pandas date time indexed object. Okay, but you may want to be able to explore your time series a bit more conveniently, rather than having to subset different intervals to look at them all. So what I like to do for that is use the plotly library. You don't want to use it if your data set's too massive or if you don't have a good laptop, but if it's reasonably good size, then you can do it like this, and not only will it allow you to read the specific values and timestamps as you hover over the figure, but also allows you to zoom, right? And then pan along and study any interesting periods in more detail. So that's quite useful. So that's just using the Plotly Python library there. Okay, now one of the initial things that we like to do with time series is to think about what are the different components that make it up. And so here are the three parts we like to look at. We have trend, which is, for example, is there an overall increase, an overall decrease over time? On top of that, is there any seasonality or periodicity in the time series? And thirdly, is there an element of noise on top of those two factors? So yeah, have a think about what you might see in our sunspot number, whether you could notice any of those there. So hopefully you would have noticed that seasonality or periodicity, yep, there we go. So periodicity comes through very strongly in this time series. As for a trend, does it look like once we account for that, sunspot numbers tend to be going up or down? If anything, they seem to be going down a bit. If you look at the peaks of those cycles, in particular, the last completed solar cycle was a particularly weak one in terms of sunspot numbers. So you could make a claim that it's going down slightly, but we'll see later on how we can quantify that a bit better. And then in terms of noise, I'd describe these high frequency fluctuations as noise. You know, clearly underlying it, there's a relatively smooth curve, but on top of that, you have these fluctuations which you would naturally expect to see. Okay, good. So now, one way of kind of just brute force hiding some of that noise and more clearly extracting what is the trend, what is the seasonality of your time series is by smoothing it, right? Now, there's a couple of ways you can do this. Well, there's many ways you can do it, but two of the more common ones are a rolling window. So this is just basically just taking a moving average of the data set, updating it as we get a new point and removing the oldest point, so rolling along like that. And the other one is simply downsampling. So this is just changing the frequency of observations in your data. And again, if you've date time index to your data frame, Pandas does this very conveniently. You just need to choose the unit of time that you'd like to resample it to, and that will fix it for you. So once we do that, we can look at, so there's our original time series in the blue, and on top of that we have in green the 12-month rolling mean. So you'll still see some variation. It still has the same number of points as the original time series, though obviously it's cut off a bit at the start because you don't yet have 12 values in your window. So that captures a wee bit more of the short-term fluctuations. And then in the orange we have our annual means. That's just from downsampling the data. So we just have one value for each year, basically. So it's not quite as smooth as the rolling mean, but perhaps that's sufficient information, and both pretty clearly remove a lot of that variation. So those are a couple of ways to kind of smooth your data and understand a bit more about underlying trends or periodicity. But ideally we'd want to quantify things a bit more, right? So two of the key statistics that we use here are the autocorrelation function, power spectral density, and then we'll come to these two assumptions of stationarity and ergodicity. So the autocorrelation function, you intuitively know about the idea of correlation between two variables ranging from 1 to -1. Autocorrelation, as the name suggests, is the correlation of some data with itself. And as we've established, because time series are sequential in nature, you're likely to have high correlation between 2 points separated by a small lag. So the tau here represents the lag or the separation between two measurements. And so we'd expect that to be high for measurements close to another. And when we normalize this autocovariance to become autocorrelation, it's forced to start at 1. You obviously always have perfect correlation with a value with itself when you have no separation. And then typically you see it drop off to varying degrees as your lag gets bigger and your measurements get further and further apart. And one way people like to intuit or kind of describe autocorrelation measuring is the memory of the time series. It's the idea that if a time series has a short memory, then the autocorrelation drops off very quickly, and before long, previous values don't inform future values at all. Or you might have a long memory time series or a persistent time series where actually your time series moves very slowly and therefore previous value almost entirely informs the future value. Okay. So, and we'll come back to this a bit later on, but in order to basically be able to define an autocorrelation in the first place, it needs to be a constant description of your data, i.e. autocorrelation shouldn't change depending on what segment of your time series you're looking at. And hence why we can define a variance for the overall signal rather than just a variance for at a specific lag. Okay. So for this, we can use the stats models package. It is convenient. And then we'll start off by just showing what it looks like for white noise. So as I said, white noise, you can basically model it as every point being independent. So in order to generate this, I'm literally just sampling from a standard normal distribution and plotting that. As you can see, it looks noisy. So what does an ACF of that look like? Well, remember it is defined to be 1 at a separation of 0, at a lag of 0. And then beyond that, there is statistically insignificant correlation. You can see it's all just fluctuating around 0. And again, that's because we haven't modeled any kind of or dependence or correlation whatsoever. That's something to compare it to. And then let's do it for our sunspot data. Okay, so here we see a very different trend, and one that again links back to that highly seasonal pattern. So clearly periodic autocorrelation function. And if we just add in, you may be aware that the solar cycle is 11 years on average. So if we just add in the lag that corresponds to 11 years, so this x-axis is in months because it's monthly measurements, I didn't mention that. We can see that first peak after the separation of 0, the first peak of that corresponds very well to a lag of 11 years, which makes sense that if you think you have a peak at one point and then you have another peak 11 years later, there's a clear relationship between those two. They're very similar, whereas a peak and then 5.5 years later you have a trough, there's a clear negative correlation between those. And that's why before that peak you have this trough in correlation showing a negative relationship between those opposite ends of the cycle. Okay, and then that continues because we have the seasonality doesn't die off; it remains very strong. So that's certainly a good clue to periodicity, though as we'll see that the power spectrum is a bit better suited to this. And yes, that's where we are now. So power spectrum is now moving from the time domain into the frequency domain. Right? So it's revealing the power or energy that you have at different scales or frequencies or wave numbers in your signal. And as you can see from the equation here, it is the squared magnitude of the Fourier transform. So Fourier transform, obviously, converting from time to frequency domain, but that still contains phase information, which isn't typically not of interest. So by taking the modulus and squaring it, we're just left with that magnitude information for more straightforward analysis. However, as part of this changing domains from time to frequency, there are a lot of issues that you need to deal with, which typically would be part of your standard Python spectral analysis functions. But these are things like aliasing. If you're not sampling at sufficiently high frequency, you'll get kind of aliasing at lower frequencies when you can't sample the high frequencies. And there's problems of spectral leakage. You might need to do things like pre-whitening or post-darkening signal. There's edge effects when the edge of your signal isn't accounted for appropriately, so therefore you can use window functions on those. So a few caveats as you go into the frequency domain, but a very useful function as we're about to see. And then you can see from the second line of that equation, it actually has a very close relationship to the autocorrelation function that I just showed you. And in fact, by taking the Fourier transform of that, we directly arrive at the power spectrum. Okay, so quite a neat feature, and that's called the Wiener-Khinchin theorem. And it's used in the Black-Minshuki method for estimating the power spectrum, but I think the fast Fourier transform algorithm has overtaken that as the most popular computational tool for computing the Fourier transform and from that the power spectrum. Okay, so that's what that's all about. So again, we'll just compute it for white noise. So yeah, using the signal package here, and what you can see, it's flat. It's flat because basically white noise has the same, all magnitudes are equally important. All frequencies are at the same magnitude rather. So there are no specific frequencies which dominate or show any kind of periodicity or things like that. So again, that's something useful to compare with. And then if we run it for our sunspot data, so here I'm just having to, see you have to specify the frequency of your measurements. So I'm just converting in seconds, so I'm just converting from months to seconds for that, and taking 1 over to get it in hertz. Once we do that, we can see our peak at again a frequency corresponding to just about 11 years. So nice to highlight that that dominant periodicity. And what's useful here is we can actually calculate what frequency is the maximum value at. And once we do that, we can get a more specific reading and find that at least for this 50 odd years that we're looking at from this data, the typical periodicity is actually a bit shorter than 11 years. And this is known that the cycles do vary slightly in length. So interesting that it's a bit shorter for this data set on average. Okay, there's the power spectrum. Again, feel free to jump in with any questions as we go. But otherwise, I'll move on to what we can do once we've confirmed what the periodic trends are in our time series. And there's this idea of time series decomposition, right? So I mentioned back when I first showed the sunspot data, trend, seasonality / periodicity, and noise. And there are functions that will do all that for you, but one nice simple illustration is we can just actually, now that we know the periodicity, which I'm just going to say is 11 years, we can basically calculate the average value across that cycle and subtract that from our original time series. Okay, and this, by removing these seasonal patterns, it allows us to detect underlying trends in the data, which may be masked by the seasonality, and also quite important for specific time series is detecting outliers or anomalies, which again can be hidden by other components of the signal. And it's also important, as we'll see, for improving the stationarity of a signal, if you can take out the trend or other large-scale behavior. So what am I doing here? I'm just defining the seasonal period in months. I am calculating how many cycles there will be in the data set, and then I am basically just truncating it. So I'm just separating the data out into intervals of that length, of the cycle length. And then I'm calculating the average across each of those cycles that I've chosen. And then once we plot that, this is what we get. Okay, so once we divide it up into those interval patterns, we see all the blue lines here in the background, and then when we calculate the average of those, that's when we get our typical or average seasonality across the data set. And as something we'll come back to later on, just notice how the variance changes. So if you look, is the seasonality have higher variance at the peak of the cycle or at the minimum of the cycle? So the maximum or the minimum, where is there more variation in the number of sunspots? And as you might notice, and as we'll see in our forecast models later on, much more variability at the maximum of the cycle, right? Does that make sense, everyone? You see just a lot more scatter around there than you do at the bottom. Okay. If anything's unclear, let me know. But so that's a great way of first modeling the seasonality, and that means we can subtract it after that. So we'll just repeat that seasonality multiple times, subtract it from our original signal. And once we do that, this is what we get. Okay, so there's our original time series at the top there. There's our average seasonality. So I've just taken that red line and repeated it to be the same length of the original series. And then we've subtracted that from the original. Here's what we get in our deseasonalized time series. And you might notice this, we still see these kind of a somewhat cyclical pattern at about the same periodicity, about the same frequency as here. So what that's telling you is it hasn't actually accounted for completely for that periodicity. And we'll see that in the correlation functions as well. In fact, I'll just do that now. So there's our original ACF. Calculated it's slightly different, which is why it kind of drops off like that. But when we look at the deseasonalized one, it's not as clean. You know, there's a bit slightly noisier and it drops off a wee bit quicker. But clearly we still haven't accounted for all of it. Otherwise, you would expect to see these cycles gone. And I think the reason for that is just the probably slight variation in the length of the cycles, but more so the variation. And you can see that in our deseasonalized time series, where it points out, so we have in this green line here, we see points far above, greater than 0 at the peaks of the cycle. And as you can see, those peaks are much higher than later on. And similarly, with that very small cycle at the peak, we've got very small values there. So even though it hasn't accounted for all the seasonality, it's still useful in really emphasizing what peaks were much larger than average and what peaks were much smaller than average. And yeah, really highlighting that 2010, 2020 cycle was a lot weaker. So that's a way of getting some kind of useful information, just doing very simple subtraction of your average seasonality and seeing the effect that has, which won't always remove completely, but it's still informative. And as I was just doing a little bit of prep, I came across the paper where in physical review letters where the first detection of gravitational waves by LIGO was announced, and they had a somewhat similar analysis in their method. So in the top row, they have the actual signal received by the gravitational wave antennas. And then what they did, instead of calculating seasonality, they compared it to their basically theoretical prediction, as far as I understand it. Very, very light reading of it, very quick reading of my part. But these very smooth curved lines in the second row are the theoretical predictions of what this black hole merger would look like. And then, similar to us, they've subtracted that signal from the original signal, and then they're left with this noise at the bottom there. And reassuringly for them, it looks pretty stationary. It looks reasonably like white noise. As it turns out, very often the noise in gravitational wave astronomy is very non-stationary and very non-Gaussian. But from my limited understanding, at least this subtraction seems to have captured the key variation very nicely. So yeah, nice demonstration of this idea of subtracting some kind of periodic or expected signal to see whether that explains a lot of the variability. Okay.
Daniel, can you go back to the slide?
Yeah, sure.
So towards the end of the chirp, there's a high frequency modes in the smoothened data. And if you look at the residual, they kind of have that frequency mode still hanging around, the high frequency part.
Oh,
Like in the
yeah,
solar
okay.
data, you have it. Yeah.
Yeah. I suppose
That,
because they're not
yeah.
removing that
Yeah,
frequency
it
from
failed
the
to remove
entire
that
signal,
part,
right?
I believe. Yeah.
Yeah, that's a good point.
I think that's a side effect of smoothing too much.
Right,
Yeah.
right. Yeah, that is true. Yeah, I'm sure there are various complications with it, but
Yeah.
uh,
Okay, carry on, please. Yeah.
no, good point. Thanks for that. Okay, so as I mentioned, to me, this residual noise looks fairly flat, and that is often what we'll want when we're modeling or when we're forecasting, is to have a time series that we can work with, which is unchanging in its statistical properties, and that relates to this idea of stationarity. So you can see here in this somewhat blurry figure that I stole from the internet is in panel A, we see an example of a nice stationary time series. And then in B, we see some different examples of non-stationarity. So one example is when you just have a trend in the data set. Another one is when you have a step change, as you can see. And then another one is when the variance or the size of the amplitudes changes in your data. So what is commonly referred to in practical settings as weak stationarity is where your mean and your variance do not change with time translation. So different parts of your signal, or if you have some long interval and you look at different parts of it, ideally you don't want one bit to have a much bigger variance, or one bit to have a very different mean than another one. Now, obviously this isn't often the case. Many real-life data sets are non-stationary. As you can see with our solar wind data set, this clearly has this, even if it doesn't have much of a trend, it's still on short time frames, the mean changes a huge amount. And indeed the variance as well, as we saw going from the minimum at the trough to the peak of the cycle, you see the variance change quite a bit. So, but often you can achieve a stationary series and therefore go on to do your forecasting in a more robust manner by just differencing the series. So if we do that for our sunspot number, you'll see, well, it's gotten rid of the kind of the changing mean, right? Now the mean is very flat along zero. However, now we really see the changing variance as a problem, right? And as I mentioned, these big high amplitude regions will correspond to the peaks of those cycles where we saw large variation in sunspot number. But especially if you have linear trends, just taking this difference, so literally just subtracting one bit the values from the previous values, this will often make your time series stationary. And that's a key part of the arena modeling, which we'll touch on a bit later. And there's also a number of statistical tests that will check for this in Python or R or whatever you're using. Can give you some significance level, whether it's highly significantly non-stationary or whether it is reasonably stationary. Often in solar wind studies, people assume it's stationary, or they'll choose to select intervals which are relatively similar. So avoid large shocks, which you occasionally get in the solar wind, or fast wind and slow wind have different properties. So you can also just segment your interval and achieve at least quasi-stationarity by doing that. But if you wanted to describe an autocorrelation function or a power spectrum and claim that it's actually representative of your data, obviously we need to make it so that the autocorrelation power spectrum isn't suddenly going to change if you're just looking at a different part. So if you want to justify using those statistics to describe your data, you really do need to at least somewhat validate this claim of stationarity. Okay. So the other one is a similar idea, but it is distinct, and that's called ergodicity. So this figure here is kind of showing how, if you remember this idea of a stochastic process where one observed time series is a single realization of a stochastic process. The value at any individual time point could have taken on a range of values. That distribution might have been wide, it might have been narrow, but it had some distribution. And every time we measure a time series, we're sampling from that distribution. And if we could measure different values at a single time step and take the average, that's what we call an ensemble average. And often you might see angle brackets, often denote an ensemble average. But often, obviously, you can't measure different values at the same time step. So what we're forced to instead is just take a time average, which is valid assuming this property of ergodicity, right? And that's what defines this assumption. The time average converges to, or is eventually the same as, the ensemble average as the length that you're averaging over. So the length, as t increases, your time average is going to converge to your ensemble average. So in other words, we rerun history with the same underlying process, we will get similar statistical properties. So yeah, the idea of stationarity and ergodicity, they're both kind of tackling this idea of how representative is your given time series of the underlying process. So I guess stationarity is, different parts of the interval, are they statistically similar enough? Whereas ergodicity is something like, are your statistics of an interval, are they going to converge to what the underlying average is? So they're similar, and that is why all ergodic processes have to be stationary, but not all stationary processes are ergodic. Okay, so that's the kind of relationship between those two factors there. And just to visualize some of what I'm talking about here, so we've already seen what non-stationarity looks like, but another non-stationary process which is not ergodic is what's called a random walk. So it's also known as Brownian motion or a Wiener process. And basically this is just, you take some starting point, usually 0, and then you should apply some random shock. So it'll be up or down, equal probability, and you just sum these shocks and then follow your time series as you do this. So therefore we can conveniently simulate it by just literally getting the cumulative sum of a white noise process. And there's an example of what this looks like. So, it'll occasionally go on these wild tangents and then hang around and then do another one. And then we can just look at a couple of these. This one's very different, goes down for a while. But if we do a whole bunch of them, we get something that looks like this. Okay, so the reason this is, well, firstly, it's clearly non-stationary, right? Like the mean goes off you've got huge trends often. And the reason it's not ergodic is you can see that as the length of the interval increases, your mean is changing hugely and your variance is changing hugely, right? The further you get away, the variance is going greater, as one might usually go positive or negative or somewhere in between. Whereas if you look what it's centered on, the expectation at each time point is 0. So the ensemble average of a random walk process is 0 at every time point. And that's the key that makes it not ergodic, is that as the length of the interval increases, the mean is changed to a huge degree. The ensemble average is always 0. And because those two one doesn't converge to the other, it's not ergodic. Okay. So that's stationarity and ergodicity, kind of two key assumptions that you need to at least keep in mind if you want to, be confident in how you're describing your time series. Okay, and this brings us to the realm of forecasting. So yeah, I'll just check if anyone had any questions so far about statistical descriptions and assumptions. There'll be more time at the end, but just let you give you an opportunity now. All right, so no further questions.
If anybody has question, can either put in the chat box or raise a hand, and I will ask Daniel to respond to that.
Yep.
Since there is nothing at the moment, Daniel, you can continue.
Sure. So yes, so we've talked about describing a time series, and often humans want to know the future, stock price, the weather, economic forecasts, perhaps less so in physics. Again, the space weather example was the one that came to mind for me. Again, that's a very human kind of practical concern. But I think it's worth mentioning anyway, because if we have a good statistical description, perhaps that means we'll be able to predict it well. And this also leads nicely into some of the machine learning approaches. So perhaps another thing which applies it more generally is that forecasting, we're trying to model what is happening in a period we have observed. That could also apply to gaps. If you have some segments of data missing and you want to make some statistical claim about it, forecasting in that case is really interpolation or backcasting or nowcasting, whatever you want to call it. So a lot of the same principles can apply to interpolation, except the difference there is you actually have an endpoint and not just a start point from your forecast. So it's bounded at both ends. Obviously, with forecasting, there's a caveat that they'll always fail when you have large shocks to the system. And if you look at any, if you imagine anyone who tried to forecast, the seasonal tourism numbers for anywhere in 2020, back in 2019, those are probably the worst forecasts they've had in a while. And the other thing you have to keep in mind is that, whenever you're testing some fancy model, is just compare it to your simplest baseline model. Typically, what that is for forecasting is what's called a persistence model, which is just saying next value is going to be equal to your current value, or current value is equal to your previous value. So you always want to include that in your evaluation, so you're not actually doing worse than the simplest possible prediction you can make. Okay. So that's an important baseline to use. Machine learning is also quite a popular method, especially for language and transformers, as I'll mention at the end, but they don't always include these confidence intervals. So that is an important caveat there. So what we'll do is we'll just go through a little bit of the pre-processing for time series forecasting. So for example, so we're using scikit-learn and TensorFlow when we get into the neural network-based forecasting models. And so what we're doing here is we're scaling the data to make it more manageable for the model. For our current neural network, we're going to need to put it into sequences so we can easily say, right, here's some training data, here's the test data, with the test data just being the next value on the sequence. And we're going to choose some length for those sequences, split the data into training and test sets based on that. and then we need to reshape it for our neural network, which I'll explain momentarily. But before we get into the fancy neural network, we'll just start off with the kind of most common fundamental statistical forecasting model, which is what's called an ARIMA model. So ARIMA stands for Autoregressive Integrated Moving Average, as you can see here. And so just what each of those terms mean. So basically, it's a combination of a linear regression on previous terms. So here we've got some constant here, and then we're going to predict the current value y at time t as some coefficient times the previous value times some other coefficient times the value before that up to p previous values. So that's just simply a linear sum of previous values. Then there's this moving average part, which is the error terms, or otherwise known as the shocks. So we also put some coefficient on the error terms, and that's called the moving average component of the model, and that goes up to q terms. And then finally is this d parameter. Now, as I showed before, we want a stationary model, a stationary time series for these forecasts to work effectively. And remember, I showed just by taking the difference of the time series, we can get rid of various trends and improve the stationarity requirements for this model. So sometimes once we'll do it, sometimes you might need to do it more than once. So this d parameter tells you how many times the difference of series before you fit the model, and thereby have a more robust coefficient estimates. So yeah, these are kind of the fundamental statistical model for forecasting. They're quite simple, fast to train, generally better suited to smaller data sets, and we're only trying to make a short forecast. As we'll see, they quickly revert to the mean of the data, so that has some limited value, but in some sense accurately represents the uncertainty as you get further out. And just like that persistence model I mentioned, it's good to use as a baseline for your more cutting edge methods, as we'll get into now. So in order to fit one of those, so the stats model library has a function for that. We're just again using train and test sets, and for this one we're going to fit. So we're going to use 2 autoregressive terms. We're going to use 2 moving average terms, and we'll go to difference of series once. That'll be something you want to do some kind of parameter search for, but just for here we're going to fit that. And very quick to run, so we'll see the results of that momentarily. Okay, so here's our first introduction to machine learning for time series. Now, the broad class of models that are used for sequential data is called a recurrent neural network. So you may know an artificial neural network in its simplest form is basically a linear regression of your input parameters, which are then fed through a nonlinear activation function, and then the results of that are passed on to the next layer of nodes, and then you have another model where your weights are multiplied by your inputs plus bias back into a nonlinear activation function, and these are just happening many, many times as you go through the layers and eventually end up with some output. Now, when you're processing image data, that'll perform a convolution over kind of various areas of your image, and will then pull the results. So you're summarizing the high resolution information to lower resolution data, and then getting your prediction about what's in your image. With recurrent neural networks, they're really focusing on, again, this autocorrelation aspect of our time series. And therefore, how they do that is using something called recurrent connections, whereby the output of a neuron at one time step is fed back into the network and the next time step. And we can see that here with our kind of schematic of an RNN. So we have our X input, our O output, and then our H hidden layers. And as you can see, the data is being fed back into the model as it progresses. And if we unfold that simplified diagram, you can see how the inputs are being fed into this hidden layer, but then the output for a previous time step, nonlinear activated linear regression, is then fed into the calculation for the next time step, and so on and so on. So this is a way of, it recalls previous information and therefore models that dependence or dependence between observations. However, you do have a problem with this model, something called vanishing gradients, where as you go too back in time, as far as I'm aware, the basic idea is that the model forgets what happens too long ago and therefore kind of loses potentially important information about earlier on in the sequence. And so the key breakthrough to deal with this problem was something called the long short-term memory network, or LSTM, and that helps to overcome this problem with vanishing gradients by using clever tricks to retain more of that older information. And interesting enough, with large language models, you may be aware that the transformer is another level of modification where the model can choose where to pay attention in some sequence, given the most recent information won't always be the most salient to your output. So it uses something called a self-attention mechanism to say, actually, what happened 5 time steps ago, whatever word that was, is more important than the word that I just saw. Therefore, I can choose that to select to better understand the meaning of the sentence. That's just a tangent on the models which are going to rule the world soon enough. So thought I might chuck it in there. So what does this look like for our data? So you can build one up very simply using the scikit-learn packages. So you can use an LSTM, use this many nodes. I'm going to feed it in those sequences I mentioned. And this will take a little bit longer than the ARIMA model to run, and we'll get some warnings here about some annoying function deprecation, but you just got to learn to ignore those. Otherwise, you're forever trying to update all your libraries. So you can specify the optimizer, your loss function, and so on. Plenty of hyperparameters to tune, as always. So yeah, again, this is being fed in sequences of our sunspot data. So we've cut it up into, we have a bunch of training data, and then the last value is the target value, the Y value, because we're trying to predict the next value. And then it is training on a bunch of those sequences. Those are all the kind of inputs, each of those sequences, and then the last value is the expected output. So bear with me why those weights all back propagate and trying to find the best fitting model. And so we'll compare that against our ARIMA model. And then we're also about to look at another model called a Gaussian process regression. Now, as we'll see, this Gaussian process model is actually, oh, there we go. Okay, that model's been fitted, so I'm not going to spoil the surprise about how well it did just yet. So as I mentioned, Gaussian process regression, it comes up in machine learning, like it's in scikit-learn, but to me it feels much more statistical in terms of how it captures uncertainty, and I think it's just a really useful way of performing any kind of uncertainty quantification in a time series, whether that is making forecasts or, as I mentioned before, performing interpolation between values that you haven't measured. So that's what I mentioned there. So it uses a model for autocorrelation via covariance matrix. And I'll just quickly bring up this nice visual exploration. It's quite a nice website here. So basically, here's kind of, the essence of a Gaussian process is modeling. Remember that distribution I talked about. You have a stochastic process, you have a distribution of possible values at each timestamp. And what a Gaussian process does is it basically collapses that distribution onto a single value when you observe a time point, but then it remains uncertain between those time points. So as you can see, it's a probabilistic method that gives a confidence for a predicted function, confidence that reaches 100% at a value observed. And as you get further from that point, the confidence interval will grow based on the autocorrelation that you specify. So if there's very strong autocorrelation, this interval will taper out very slowly. But if there's very low autocorrelation, you're going to be uncertain as soon as you move away from your observed points. So that's something hopefully we'll be able to visualize. But here you can see how it works. As we observe points, we become more certain about where the function lies, but there's still some degree of uncertainty between those. And the key problem in fitting a Gaussian process or performing Gaussian process regression is choosing how wide should these intervals be, and should they show any kind of periodic shape or things like that. Okay, so I'll just see if there's any other sort of values. So yeah, we're modeling our time series as a multivariate normal distribution. Okay, so it has a vector of means at each timestamp and has a correlation matrix, basically just describing that autocorrelation that I showed you before, how closely are two values related to one another. So there's some nice visualizations in this document that help explain that. So worth having a play around with. Yeah, this is concepts of marginalizing over distribution and conditioning on a distribution. So that's what we see up here when we select a point. We're conditioning on that point, and our distribution will respond as we do that. And here, I guess we're showing, yeah, as we move along that correlation matrix. So if 2 points are highly correlated, they're going to be very similar to one another. But if they're very different, then that has a low correlation value. So that's just showing how two-dimensional normal distribution relates to how we model the similarity between 2 points. So there's some more of that there. And then here we can see what are essentially two-dimensional autocorrelation functions. And we can toggle the parameters here. So these are not normalized to 1, like I showed you with autocorrelation. So they're autocovariances technically. And basically, if you think about how long the autocorrelation takes to taper off, that's what we're defining as the length here. So for white noise, for example, we've got perfect correlation along the diagonal because we're just where it's just correlating with itself at the exact same time point. So that's perfect correlation. And then we have zero correlation elsewhere. So remember, that's what we saw for our autocorrelation function was 1 at lag 0 and then went straight to 0, or lags greater than 0. So then when we're modeling a Gaussian process to try and represent uncertainty at time series, we can choose this length parameter to basically define the strength of that autocorrelation. As we increase it, we're getting a more persistent time series, we're getting a longer memory time series. Therefore, you can imagine the autocorrelation dropping off more and more slowly compared with the white noise model. But then you remember for our sunspot time series, it didn't drop off smoothly at all. It was wiggling all over the show because of that 11-year cycle. So we can account for that as well in a Gaussian process by using a periodic kernel, as it's called. So kernel is just our model for autocorrelation in a Gaussian process. And similarly, we can choose how variable is the data, how quickly does it drop off, but then for this one, what is the periodicity of the data? So periodicity P determines the distance between repetitions. So this is all accounted for by carefully choosing the appropriate kernel. And we can see that here. Can we add points? Oh, we can add points. So this is just our very boring, I think, radial basis function that stands for. So just if you have a smooth drop off. And I think hopefully we should see as we bring this invariance down to 0, it looks a lot like white noise. It does indeed. In fact, it's just entirely flat. So very boring. Oh, no, my mistake. I mean, as I bring the length down to 0. Okay, so the variance is just the variability of the series, which is independent of its autocorrelation. So if we bring the length down to 0, there we go. There's that white noise looking signal because we have 0 correlation on the off diagonals, which again is just like that white noise autocorrelation function where it drops to 0 straight away. And then yeah, this just changes the amplitude of that. And as we bring in that autocorrelation, suddenly this time series or stochastic process in this case is much smoother. Okay, because we have a longer memory time series, it's more persistent, and future values depend much more strongly on previous values as a long memory. Okay, so yeah, Gaussian process, really nice way of kind of bringing together some of those time series concepts, really. And here is telling you a bit more about how it predicts what the distribution will be, conditional on some observed value. It basically just reads off that correlation matrix, right? So basically, if you have some point and you want to measure and you want to know what the distribution will look like, say 10 points away, so you'd go down to here and then measure what is the correlation value at that point. And that is how I'm going to adjust the distribution based on whatever that value is. And Gaussian processes kind of have a Bayesian flavor to them. So this is called the posterior distribution once we've observed those points, which are kind of like our when you observe the data, we have some correlation matrix, which is our prior distribution. We observe some points. Oh, this is going to demonstrate just what I was saying. So we observe some points, and then we update our prior based on the observed data, and then we obtain a posterior distribution for our time series likelihood. Okay, and then this is, I guess, is just showing how when we observe points, the variability drops to 0 at those different distances because we've observed the point. So we have 0 uncertainty. Again, here's our different kernels. So obviously we want to use a periodic one for our data that we're using here. And then again, just some nice visualizations of how that distribution updates based on both our covariance, autocorrelation kernel, and the observed data. Okay, so quite a powerful statistical/machine learning method for capturing uncertainty in the data, both representing uncertainty between points, but also, as we'll see, in predicting future points. Okay, I guess I could have run this while we were waiting, but I feel like this one is reasonably quick. Let me see if this is anything interesting. So yeah, scikit-learn is a nice demonstration as well about choosing your appropriate kernel, capturing that periodicity properly. Yeah, so they're using a sine squared kernel to capture that there. Okay, that's done. Okay, good. So now we can actually compare these various forecasts. And so there's a quick look at them there, but hopefully this is still working. Yes, it is. Okay, now we can, so I'm using Plotly again because I really want to zoom in to study our results. So yeah, here's the rest of the data that the model was trained on. And in this period here is the forecast period. And therefore we can actually compare what we observed with those model predictions. So if we just zoom into that. So first thing to pull out is this, actually let's keep the test data. Oh, I can't get rid of that, that's fine. So if we just focus on the green line, this is our ARIMA forecast, right? And as I mentioned, quickly reverts to the mean. If we look at this period here, actually maybe this will be good. Zoom out a bit. Let's do that. So it does capture some of that decrease that we observed, albeit in a very smooth kind of average sense. But then it does quickly flatten out because, as I said, ARIMA is very mean reverting. However, I could have improved it by accounting for the seasonality. I only used that 212 parameterization. I haven't actually factored in enough of a memory into the ARIMA model to allow it to capture the periodicity. Basically, all it's aware of is that there is recently a decreasing trend, so it's probably going to decrease a bit more. So if you were to play around with the ARIMA model a bit more and use something called a Sarimax model, you can incorporate that seasonality. But that takes a long time. I wasn't able to fit it going back, 132 months to capture that cycle. So perhaps the data is a bit big. As I mentioned, this ARIMA models tend to be better for smaller data sets. Okay, so now that we've looked at that, let's bring in some of our other ones. So if we look at this one here, so this LSTM is our, if you remember, is our long short-term memory machine learning prediction. And gotta say, it does pretty well. Seems to have learned the general trends. Obviously, doesn't pick up some of these peaks perfectly well, but certainly captures that seasonality very nicely. And then finally, if we bring in this orange line, so this is what the shaded region corresponds to, because of course, as you've just seen in many times, Gaussian processes intrinsically capture the variation, right? They give you a distribution between observed points, which is what we're seeing here. And yeah, perhaps if we compare it, like it doesn't match quite as well, and we'll quantify that in a minute. What I really like about the Gaussian process regression is how the changing width of that confidence region really reflects the changing variance that we know from this data set, right? Like if you think back to when we overlaid all the cycles that we observed, and we saw that there was a lot of variation at the peak of the cycle, but very little variation at the trough. I think that's just captured beautifully in the Gaussian process regression, right? When we get to the peak of the solar cycle that we're currently in, there's a wide range of possible values that it's given at the 95% level, whereas down at the trough, it's really shrunk that uncertainty. You know, it's much more confident about the number of sunspots that will occur at this at the solar minimum. And in fact, you could just very simply improve the model even further by telling you you can't have negative sunspots. So that's another thing to always be aware of. Like, is this physically possible? If not, can I improve the model just by setting a rule that you can't have unphysical negative sunspots? And I'll mention at the end, this kind of comes back to this idea of physics-informed neural networks, or physics-informed machine learning. We're actually using a bit of, in this case, basic common sense, or in more sophisticated cases, physical equations for what we understand about the process, combined with this power of, huge data sets and nonlinear processing. Okay, so that's 3 different models. One kind of basic statistical model to use for smaller data sets. One that has more of a machine learning flavor, but still really represents the uncertainty nicely, which isn't always the case with machine learning. Often it'll just spit out a number and not give you any kind of distribution or error bars. And then finally, our recurrent neural network model, which is kind of more the epitome of machine learning. So yeah, what do you notice about the confidence interval? So I mentioned that and how it compares with that mean seasonality. So a nice capture of uncertainty there. And of course, we want to put some numbers on those predictions. And we can use a couple of different metrics. And in both cases, though, the recurrent neural network comes out on top, the lowest error in both cases. Is that enough of a gain over the uncertainty you get with the Gaussian process? I'd probably say no, but if you're purely interested in forecasting accuracy, then it seems as if that's the way to go. Okay. Can we say that ARIMA may be more useful for datasets which change quickly?
There is a question. Yeah. The chat box.
Yes, yeah, I just saw that. Yep. Maybe more useful for datasets which change quickly. That's an interesting question. I think a dataset that changes quickly is always going to be difficult for any model to measure accurately. I would assume that ARIMA is actually a bit of simpler data, but if you can expand on why you think that might be the case, I'd be interested to know why. Yeah, it's a good question. I'm just it doesn't immediately seem to me that it would be beneficial.
And Daniel, if we use the ARIMA after removing the seasonality, won't that capture and then add the seasonality later? Won't that capture it better? Is what my understanding.
Yeah, exactly. So that is part of kind of transforming the data before you fit a model is particularly important for ARIMA, which is not only you're making it stationary but accounting for that seasonality. So yeah, there is a model called SARIMA. S is for seasonal. So yeah, exactly. You can simply remove it, make your predictions from the stationary series, add the seasonality back in, and that is how I think often with the economic forecasts, which have a seasonality, is they'll do exactly that. So yes, that is an important part, which is I just haven't done here.
Yeah, the other thing we can actually see, and then in the equation and also in your prediction as well, and that's essentially that ARIMA cannot go really far out in time, just because of the way the equation's written out with certain number of parameters from back and stuff, right? So that essentially the memory issues in there, right? So Because of that, the ARIMA cannot go really far out. It's going to diverge very quickly. So maybe the seasonal ARIMA things that you're saying, maybe they improve these things and better. But the one that you showed, right? I would say, instead of saying changing quickly, to Harkirat's question, right, I would say like short-term forecasts
Mhm.
would be kind of a more appropriate way of thinking about it.
Yeah, that's a good way to put it. Absolutely. Yeah, and as I briefly mentioned, that is tend to be where they're used. Whereas I guess these machine learning models, if they're trained on multiple different sequences and um, they're long enough to capture the seasonality, then they can do that pretty well, because they're fed that entire data set rather than just two or 3 or 4 of the previous values like the ARIMA model is forced to do. Yep, no, good comments. Yeah, so I will just then, was there another question? Is that just background noise?
Yeah, I guess you can carry on. Yeah.
Okay, sweet as. Yeah, so statistical description, forecasting, and then there's this issue of noise, which I think is particularly pertinent to astrophysics. I don't actually have a huge amount to say on it, unfortunately, but I do have a little bit. So obviously, the signal and the noise, we're trying to get one from the other, and we can quantify how difficult that may be by using the signal-to-noise ratio, which is typically, I think, expressed in terms of the power of the signal, but you can show that that's can basically be calculated as the variance of your signal divided by the variance of your noise. And we can simulate that, for example, just adding, we started with our original sunspot number, and we, for some reason, decided this was a much noisier signal. You can see it starts to hide some of the periodicity. Obviously, again, going back to the physicality problem, this is going to give us some negative sunspot numbers, but if you just ignore that and think about this idea of the level of noise and how that makes things difficult, you can show that point there. And effectively what I'm doing here is a very kind of rudimentary Monte Carlo simulation, right? So we're just simulating what the data could look like and then maybe drawing some conclusions about how that affects various statistics. So that's what looks like our sunspot data, but I've got another example, I believe, now going to solar wind data. Yep, okay. So I'll now show a couple
One
of
minor comment, Daniel.
Yeah.
So in Gaussian, the problem is that it can go both positive and negative. But since we are counting the number of sunspot, want Poisson distribution be more relevant?
Yes, that's a good point. Where you want some count, count noise that is only positive. Yeah, that is true. And I was talking to my colleague recently who works a lot with astronomy data, and where you're counting photons, measuring some distant emission from a galaxy or something. And
and same in particle physics, we count events. Yeah, so it's all Poisson processes.
Yeah, right. I guess same with particle detectors and of any sort. That's the typical noise. Yeah. No, good point.
Okay.
Yeah, go on. Sweet. All right. So yes, different type ways of modeling noise, and I know I'll mention this in a minute, but I'll briefly now turn to so we've had sunspot data, so still sticking with the sun, I'm afraid, but now looking at a very different type of data from the sun, which is time series of the magnetic field. So as I mentioned at the start, there's this constant stream of particles from the sun, which carves out this bubble in the interstellar medium called the heliosphere, and you see different parts of that there. This is the heliopause, so the Voyagers are out here, and this is where the data is, as I said, lots of gaps in it, a lot of noise. But yeah, we often take the magnetic field time series and perform analysis on that. So as an example, we'll go from the opposite end of Voyager. As I remember, obviously, when he was advertising my research, made some cricketing analogy about PSP being on one side of the cricket pitch and Voyager being on the other. I forget the exact numbers of that one, but here's magnetic field data from much closer to the sun. And yeah, so I've got the radial component there, and you can see, does anyone notice any, or how would you describe that data set? We're thinking about our trend, periodicity, and noise. Does anyone have any comments on what the magnetic field looks like?
Any comment from anybody?
And
Yeah,
if
it
you
looks
don't
right.
see a specific component, then that is something as well.
Yeah.
So yeah, it is a time series. So we're measuring basically from point in space, and we see some fluctuations with that. So it is, as we'll see, it can be described as turbulent. Yep. Any other observations?
I would say there are quite a few step jumps.
Right.
In the
Yeah,
data.
exactly. So you see some, hopefully, yeah. So particularly there's a jump here, another one here, smaller one over here. So it's definitely not, there's no strong periodicity like we saw in our sunspot data, but it's also not just noise. There's periods where it's quite flat, so strong autocorrelation, then suddenly there's a big jump or a moderate jump. And there are various possible reasons for these. You might get a large one as you get a CME pass through or some other kind of shock or disturbance to the flow. Sometimes you'll see more of a step change where the magnetic field changes direction and stays like that for a while. I think those can be associated with when you're crossing between different sectors or regions which have a different facing magnetic field. And also you have fast and slow wind interacting with each another, so you get these interaction regions there. So yeah, various reasons why you can get kind of more abrupt changes in magnetic field strength. Though it is typically, we won't just be looking at one component, we're looking at all three XYZ components and the magnitude, and that'll let us figure out a lot more clearly what might be causing some change. Okay, so that's a few minutes of PSP. This is very high resolution data that it's capturing. And if we just plug in our statistics again, we can see it's a lot, fairly noisy autocorrelation. It drops off kind of quite smoothly at the start, but then we see, a lot more jumps. I should point out that we're this is really computing it out too far. If you can imagine this very small sample size at the end. So typically it would probably only go up to something like 0.2. Yeah, typically it would only go up to something like that, given we want to have significant sample size at each lag to actually be robust in what these values are. And here, particularly as you look to about up to a lag of 400, you see quite a smooth, theoretically exponential drop-off in autocorrelation as you get further away. And what that might tell you is that at this distance where it drops off, if we were to assume that if we had a big enough sample size it continued flat, then we would say that beyond a lag of 400, fluctuations in magnetic field aren't correlated anymore. They're independent once you go beyond that distance. And that is an important parameter in turbulence because it basically tells us what our largest eddies are. If you imagine, if you can imagine these swirling eddies in a flow, or what's the other word for turbid, or vortices. If you imagine these swirling vortices in a river or in the wind, within that vortice, fluctuations can be correlated because they're in the same mass of fluid. But outside of that, unless there's an even bigger eddy, they're going to be independent of one another. So this point where autocorrelation drops to zero, or some point before that in practice, actually, but as it drops off to some insignificant value, that's how we describe the outer scale or the correlation scale of our turbulent flow. So this statistic has particular theoretical significance for the study of turbulence. And if you have an outer scale, you can also use that to calculate a Reynolds number. So very, very useful for that reason. And then just as useful, however, or probably more so when you're talking about turbulence, is the power spectrum. So here we have it here. What would you notice about the power spectrum? Are there any, if you compare it to the sunspot one, are there any particular dominant frequencies like we saw in the sunspot one, or is it much more kind of just a broadband spectrum? So, yeah, I mean, if we think back to the sunspot one, there's no marked jumps like we saw at the 11-year. There's a couple of jumps here, but there's also plenty down here. So this can probably be reasonably attributed to just random fluctuations and not any significant periodicity. So yeah, it's basically kind of just this decreasing function of frequency, which shows that most of your energy is at the larger scales, and it's progressively less and less at smaller scales. And what we do for turbulence is we compare this spectrum with a theoretical turbulence scaling law. You may have heard of a mathematician called Kolmogorov. So back in 1941, he came up with this theoretical self-similarity between different scale, or self-similarity in the transfer of energy in a turbulent flow from large scales to small scales, and he showed that this would result in a negative 5/3 power law. And you can see that for at least part of this spectrum, it does seem to approximately follow that 5/3 slope. So the universality of this slope in the solar wind has been one of the key pieces of evidence that it tells us that it is turbulent. And then you can see it gets a little bit steeper, but then it actually starts to flatten out. Okay, and if you think back to what I was talking about before, can you think of any reason why the spectrum might flatten at high frequencies? Do you think this is something physical or is it something else?
Daniel, you might want to highlight that flattening at least with your mouse
Oh
or
yeah,
with something.
yeah, sorry. So yeah, we've got this approximately 5 thirds power law, then it steepens out, which is what we expect to see with as we get to smaller scales, around the scale of ions and things like that. But now suddenly it appears rather flat. Now, do we remember seeing a flat power spectrum previously in this my long lecture? Maybe it's something to do with the instruments that might be resulting in an artifact in the data. But what exactly might be the cause of that?
Anybody can guess among the students? Maybe you can answer, remind them, because I think it was quite roughly more than an hour ago. Yeah.
Yeah, fair enough. Well, I'll make it abundantly clear very briefly. Maybe I'll just do that now. So yeah, what I'm about to show is that this is probably an artifact and not a real physical phenomenon or aspect of the turbulence. Well, yes, there's the operative word here. And I'll prove it to you, just so I'm not making it up, by if we artificially add noise. So again, perform this kind of Monte Carlo-esque simulation, even if it's just one. So here's in dark blue, the Parker Solar Probe data. I've just artificially added white noise, which in the case of the magnetometers on board spacecraft like PSP is a fairly representative model for the kind of thermal noise that a magnetometer might suffer from. So it's pretty even. It's independent of the value, so it's constant. It's independent of the data itself, and obviously makes the time series look noisier. Now the question is, what does that do to the power spectrum? Okay, so in grey is the original spectrum. In red is the spectrum of the noise itself. So remember we saw this an hour or so ago. We calculated the power spectrum for noise. It's purely flat. There's no, all frequencies have the same amplitude. And then when we calculate the spectrum from the this blue line, so the time series with the noise, what we get is the black line. So hopefully that makes it quite clear, this effect of noise on flattening the power spectrum is specifically at those higher frequencies, right? It doesn't really do much at the low frequencies because noise itself is, well, I guess it's where you get this overlap, right? Basically, where the amplitudes or the power of the white noise itself intersects with the original power spectrum, suddenly it's becoming this mixture of the two. And in fact, it's kind of becoming a piling noise at those highest frequencies, right? So I guess it's some kind of convolution of the two spectra is what we're witnessing there. And this is the idea of a noise floor. If you're talking about various instruments for measuring signals, you might hear this idea of a noise floor. So yeah, it's given the noise, you can't really interpret a spectrum be above some certain frequency. And you may have also heard of the Nyquist frequency. That's kind of like a kind of original limitation on frequency, and this kind of just gives you even fewer frequencies at the high end that you can study because of the effective noise. So yeah, for all of you are going to be analyzing stuff, analyzing signals with noise is something you have to worry about. And also, as Ritesh mentioned, what is the actual appropriate model for that noise? Is it white noise? Is it simply mean of zero, constant variance, independent of the signal itself? Should it be measuring count, in which case should be Poisson, or is it not stationary or Gaussian at all? And apparently that is very common in gravitational wave astronomy, is that you'll have complicated noise patterns which you somehow have to deal with. I think that might be it. So I have a couple of kind of thoughts now about the use of AI in physics and machine learning in physics. So slightly separate from the content, but it's just something I've thought a lot about, so it might be useful. And then I'll be happy to take questions for as long as you need, show some more examples of some solar wind data analysis, if that's interesting, some useful Python functions, and then we'll go from there. But yeah, so just a brief mention again, because there's a lot of machine learning in this workshop and it's something you'll be thinking a lot about. I think for me, the key thing to keep in mind is how important is that we can interpret the results of this model. Is it only, do we want accurate predictions? Do we just, if we're studying thousands of galaxies, do we just want it to automatically classify what shape they are, so then that we can study the unusual ones? So therefore we don't need the model to understand the physics, we just need it to be able to quickly sort and pick up interesting ones for us, the physicists, to study? Or are we relying on the machine learning in a more fundamental way that means that being able to interpret the coefficients or the weights or the training is much more important? So I think you should always keep that in mind about what is the purpose of this model. Are you just using it to try and get an accurate forecast? Do we need uncertainty around that? It's not always that you just throw the fanciest model at something because it has amazing accuracy. Actually think about what you want to use it for. And this kind of leads to this idea of physics-informed machine learning. So this thing that has certainly been tried a lot, you might hear about it more, is that instead of just using the standard loss functions or activation functions or what have you in your model, you actually insert physical equations based on relationships between variables into the model, and therefore hopefully not only be able to interpret the model in a more physical way, but actually get better results, because it's not just blindly learning the data, but it's actually using something about the real world. Maybe it can't learn, maybe it can learn. These things can learn in physics on their own, supposedly, but if we can program it in there, we can be a bit more confident about it. And then, of course, there's the other use of machine learning, which is just asking LLMs about code and about concepts. Again, separate from the topic of this workshop, but something that I have strong opinions on, so I thought I'd mention it. Huge gains of productivity that I myself have experienced. Just if you want to code something up quickly, but you can't be bothered looking at documentation, it's just a godsend in terms of pulling up some fancy plot quickly if you don't want to scroll through Stack Overflow, assuming you're asking it the right questions and give it the necessary context, obviously not trusting it blindly and all of that. But also, what do you lose? You lose a deep understanding of the code or the problem. So, choose wisely on what problems it's fine if you use it for, and what problems where you actually do need to do the work yourself to understand it. So yeah, there's some bonus thoughts separate from time series. That's most of what I have. As I said, I'm happy to show a bit more of solar wind exploratory data analysis, but I thought I should probably check in on questions first. So fire away.
So over to the students now. Thanks, Daniel, for this nice exposition. So I will request students to raise questions. First of all, before they ask anything, I would request you for the PDF of the slides and the notebook, the code notebook that so you can send it to me by email, which I will make available for students to practice, and also at least one sample data so that they can play with. Yeah. So physics informed, there's one question in the chat box. For physics informed machine learning, what kind of loss functions are typically used? So from my point, I can say that it's dependent upon the physics itself, but I'll let Daniel answer it.
Yeah, I think that's true. I think it depends on the specific question you're trying to ask in terms of what equations are relevant, but also, what can you easily code into a model to make it quantifiable easily by that model. And my limited experience I have with this is when you're trying to do engineering, so when you're trying to design a 3D printed part and you want to so the model that I was looking at was called a super resolution model. So you're trying to optimize the design of some 3D printed part for a spacecraft or a satellite or whatever, and you don't want to run the whole optimization procedure because it can take months. So you just run a very low resolution optimization, and then you get a CNN model to increase the resolution and give you the full optimized design. Now, nice idea, but what about when the model gives you a non-physical design, like there are two pieces of material which aren't even connected, right? So that was something where I tried to incorporate some physics into the model. So you basically went into the weeds of the PyTorch functions, found out where it's inserting its loss function, and then actually coding in what do we know about how you calculate the strength of some material. And so we actually inserted that equation to the loss function, and it had some success at improving the prediction model, but it was very difficult. Like the optimization, the training curves and everything else was quite difficult to get it to work properly. So
for example, in the case of number of solar sunspots, we can heavily penalize the negative values.
yeah,
so that's one way of saying that physics demands, or even the common sense demands, the number of spots has to be a positive integer at worst 0. So so there we can penalize any negative values. So these are the ways we impose physics, either as a limit or as an equality.
Right.
Another example that from Daniel's research that we've done is when you're trying to train neural networks to predict turbulence properties, right? You have to think about, okay, my time series, when I think about time series close to the sun, the correlation time is going to be very different versus, let's say, you're away from the sun, your correlation times are going to be very different. So you prepare your data informed by the physics that you're interested in, so that you say, okay, I'm going to prepare my data according to what I'm interested in. So when you feed it in, so you can process your data accordingly. You can use different loss functions. You can use equations and other constraints as well. So here's an example that Daniel can talk about.
Yeah, so that idea of kind of standardizing the input data, whether that's for a machine learning model or whether it's just for a simple statistical average of different errors, it's important, when you do have such different systems, that you can standardize it. So as I showed you before, talking about calculating the correlation scale, we can then use that to define the total length of the interval that we feed into the algorithm, and also the magnitude, so we can standardize that as well. So yeah, there's definitely some relationship between, I guess, data transformation and physics-informed machine learning. Like there's some overlap in the approach or the concepts there that I think is useful. So yeah, constraining the equation for the phase space of the model, yeah, I'd say that's that you could describe it like that.
So good. So any more questions do we have? It can be from the earlier part of the lectures as well. I think if you have questions, then quickly raise your hand. Okay, so there are, okay, there's another. So is there any scope of time series and forecasting for collider data? I can tell you from my side, no, because each collider event is independent of the other one. So there is no time series. However, what is time series in the collider, I can tell you, we don't have that data, which is the tracking data. So tracking data comes without the timestamp. So if we had the timestamp, our track reconstruction would be very accurate, and that way reconstruction of various events and noises in that will be very, very accurate if we had the exact timing information of when a particle crossed a particular tracker layer in the collider. So we don't have, so all I can say at the moment, no, we don't have that. But there are some other stuff you can do. So not really time series directly into the colliders per se. No, it's mostly applicable in astrophysical system where various responses are observed as a function of time. Some of the cases, arrival timing of particles and a time series of arrival timing can also play a role, but that's also used in astrophysical scenario like neutrino physics also. Yeah, so that's all I have to say about that. Okay, so Sambit Sarkar says, if you could measure timing of each particle falling into each cell or capture HDCal, time series analysis can be help point to the direction of primary particle. Right. Uh, to get the direction right, it's sufficient to know all the points. We don't need the timing information. But timing information will help us clean the signal from the background. Because when a particle hits a part of the detector, it creates a secondary radiation, which is typically slow. So if that radiation hits another part of the detector, so that will be out of time sync. And if you have the timing information, you can remove those data and have a much cleaner sample using time series if we had the timing information available. Yes.
Sorry. So is this autocorrelation is most important part of this time series data? So whenever this autocorrelation is there, then you should apply this time correlation, right? This time analysis.
Some kind of autocorrelation, if there has to be some correlation, some structure in the data. So autocorrelation is one way to measure it. That is there something worth looking. And typically time series means that you want to study the spectral function, you want to have some kind of predictive stuff. So that's where the time series data, mainly in astrophysics, appears. Some voice is coming from you, Partho?
Yes. So in collider data, mostly we don't have that kind of stuff.
Colliders, at the moment, we don't have it. But once there is enough timing layer, one can clean up the tracking part. One can clean up the tracking. That's all. I mean, it's a improving your quality of data that you can have. Okay, but it is not in the direction of predicting, as most of the astrophysics data also have this ambition of predicting something. Those things will not be there. Or even like using a time series, we will not much. I don't know. You may be able to understand the detector response, but if you understand the detector response using time series, you just have to remove the unnecessary parts. So that those things, those analysis can be done if timing information is there. Right now we have X, Y, Z and energy, how much energy is deposited in different components. And if we have timing information, that will be fifth dimension to the data, and that will be the really, I mean, useful piece. Yeah. So anybody in astrophysics attending today? Anybody working in astrophysics? There were quite a few students from astrophysics. Do we have today? Maybe astrophysicists are far more convenient, comfortable with time series than the colliders. That's why the questions mostly coming from what we can do for the colliders. We can, but only when our detector is equipped enough to do that. And the way I see, I might be limited in my imagination that we can only do cleaning of the data using time series. Because the particle is propagating in 3 dimension, their path is kind of known, so you also can predict. But if there are other things, deviations from that would be considered as a noise. So track reconstruction. Shilpi is just to add that time series can be used in pulse shape, e.g., distinguishing between EM pulse from noise in EM pulse. Yeah, so this is again noise reduction, if I'm not wrong, Shilpi. So this is basically time series are useful in colliders because the signal we are looking for has a very characteristic shape. Anything else is noise. So knowing that exact time profile, I won't say time series, I would dare say time profile is important, and those analysis is done. So yeah, exactly. So the astrophysics is the best use case, but we have all the detectors responses, time responses of the detectors are well known, well studied, and any deviations from those are typically handled in a way that those are noises. So the hardware level itself, reconstructions are done.
Yeah.
Yeah. Okay.
Thanks.
Any more questions we have or comments?
Is
Okay.
ergodicity and stationarity always assumed? Shouldn't be. Maybe it is too often by people doing this analysis that they just kind of wave their hand and say these things are assumed. You should check. If you can't, guarantee it, that doesn't mean all your results are invalid. It just means you should be very cautious about interpreting your results and saying actually the results we got from this interval might not necessarily apply for the entirety of our data. So if you can at least have some approximation of the extent that they apply, and if you can do something about it, like that differencing, or by removing non-stationary parts of it, then that'll make your results more robust. So yeah, they are often assumed, but if you're being careful in your analysis, you should at least verify whether that's the case. And if it's not the case, then add that as a caveat and caution, over interpreting the results is what I would say.
Yeah, and I think we should. The last part that Daniel said is extremely important to actually check it, right? And then it's always like, even like in solar wind, people, for example, use these approximations quite a lot, but that's because there have been papers going deep into the stationarity and ergodicity of these signals. Even after those papers were written, right, over and over, people still question this in our fields. every few decades there's a paper or two questioning the ergodicity or re-examining those issues. And in our field, in solar wind, it's kind of reasonably well established, but anything you do, you always check for these things. And visual inspection of your time series and like autocorrelations and stuff, all of the kind of statistical analysis that Daniel has talked about, they help in trying and quantifying some of these things.
So, Daniel, you are at just the right slide. I had a question about, and I forgot
Good.
when you were talking. So my
Oh, no.
question is that this E of F that you have defined on the first line, it's definitely a real number, but in the second line, in general, it's complex number. Is there some additional assumption going on that because R is real, capital R in the second equation?
Yeah.
Is a modulus put at the right place is where I was wondering.
Yeah.
Or maybe in the second case, it's only the not exponential, but cos only the real part.
Yeah, possibly.
Yeah, typically for the second equation, the imaginary parts are neglected, and they're very small, as best as I know.
So basically, it is the kind of the real part over there.
Yeah, I have to go pick up my bachelor's copy of my bachelor's book again to refresh that.
Yeah.
But that's my vague recollection right now.
Yeah. Because it bothered me, but then I did not stop the momentum at that moment. Yeah.
Appreciate that,
Didn't
because
look like that very consequential. Yeah. Then I almost forgot that I had this question. Anyway, so I will now stop recording it because there's not many questions left. And